As the internet moves out of cyberspace and into the real world of things, we're discovering that the world is often a lot more resource constrained than we'd like it to be. All those devices out there in the Internet of Things sometimes have limited battery, they have limited compute power, and it's sometimes tough to kind of extend the internet out into all those real world devices. And today we're going to talk about some of those engineering protocols and solutions for long-range networking in these limited environments. Welcome to IBM Developer Tech Talks. My name is Calvin Powers. I'll be your host. This week we're doing all those devices out there. Whoa. Sorry about that, folks. Anyway, as I was saying, this is IBM Developer Tech Talks. And our guest today, our speaker today is Kalonji Bankole. He's one of our dev advocates. He's based out of San Francisco. Kalonji, welcome to IBM Developer Tech Talks.
Thank you, thank you.
Tell us a little bit about what you do for IBM.
Sure. So yeah, my name is Kalonji, and I'm a developer advocate located in Los Angeles. So my background is mostly cloud computing, and I do a bit of IoT as well. And so I've spent a good amount of my time creating demo apps for some of the emerging technologies. So for example, AI, IoT, and blockchain.
Terrific. Oh, well, a man of all trades then. So that's great. Now, before I let Kalonji take over and walk you through today's presentation, I want to do just a little bit of housekeeping. If you're watching this presentation on the YouTube page, feel free to post your questions for Kalonji in the YouTube chat on the right there, right of the player window there. I'll be monitoring the chat and forward your questions on to Kalonji as appropriate. Also, I want to call your attention to the description field, which is immediately below the player. The first link in the description field will link to the event page for today's Tech Talk. And on the event page, we'll have lots of getting started links, and that's also where you'll be able to watch the replay and things like that. It's not up there right this minute, but hopefully by the end of this webcast, we will have Kalonji's slides up on that page as well. If it's not at the end, it'll be there shortly after. So again, feel free to visit that event page. The link is the first link in the description field underneath the window player. All right, so with that housekeeping out of the way, Kalonji, what do you got for us?
All right, sure thing. So I'm going to start sharing my screen first and play from start. Okay, so this project is titled Build a Smart City IoT System Using LoRaWAN. And essentially, LoRaWAN is a long-range wide area network. So it's a relatively new wireless protocol.
Hey, Kalonji, you need to click that hide link there on that pop-up window at the bottom.
Okay, gotcha. Okay, cool. Okay, so just to get started, just a really quick overview of what IoT is for those of you who aren't as familiar. So one definition of IoT I saw online that I really liked was it's essentially connecting everyday objects to one another and basically enabling them to send and receive data to one another. So it doesn't really matter like what kind of thing it is, like that might be a fitness tracker, security camera, television, whatever it is, as long as it can connect to the internet or communicate with some gateway that does have internet access, then it can become part of this vast IoT network. So it's really just like all about orchestrating how these devices interact with one another. And so one of the reasons this field is becoming so popular is because hardware such as sensors and microcontrollers have recently become very affordable. And another reason is the vast availability of cloud services. So whether that be databases, artificial intelligence, SMS integration, and so on. And so just moving forward, so I took particular interest in IoT for smart buildings and on a larger scale, possibly smart cities. So kind of to set the background, the use case I wanted to implement was more so a smart building idea to help with property management. So the goal was to be able to place sensors around the apartment building to passively collect information and essentially try to look for patterns in data so we could detect issues early on. And so, and another thing we were focusing on was we thought it would be a good idea to set up a system to essentially like detect motion for security purposes, and also to detect water and gas leaks as soon as they happen. So when planning out the build, I kind of had to consider what kind of sensors I'd like to use. So for this particular smart building use case, I opted to grab a few flame, smoke, sound, and motion sensors, and those are mostly used for security detection as well as potential fire detection. And also for utility monitoring, I chose a few sound, vibration, air quality, and humidity sensors. So I pretty much just got like a variety pack. Okay, so after determining exactly what kind of sensors I needed to deploy, the next step was to choose a wireless communication protocol. And so, in other words, like how can we get data from sensors out in the field up to cloud for processing? So while looking at each protocol, I had to take a few things into consideration. So first, there was, of course, battery usage. So, of course, I wasn't expecting like all these sensors to be hardlined or like connected to power. So a lot of them will probably be like battery operated, like if they're just like in the hallway or underneath the apartment building on the roof, etc. So obviously, I prefer to not have to change that battery very frequently. Another thing is the topology. So essentially, basically like how you deploy your wireless communication devices. And in general, the most popular topologies are mesh and star. And I'll get into that in the next slide. Also, security. So essentially, I want to make sure my messages don't get intercepted. Also, range. Basically, how far away can I send my sensor data? And this is pretty important because, well, for example, like most Wi-Fi devices, like they can't reach like more than 40, 50 feet. So I just like wanted to make sure that I could send my data far enough. And also bandwidth. So essentially, how much data can I send at a time? So this is just a picture, basically like comparing two of the popular network topologies. So I saw that the majority of the protocol types were offered in one or the other. So essentially, star topology is a network where all data is sent and aggregated to a central location, a central node, and a mesh network is more of a peer-to-peer network. So essentially, I chose not to go with Zigbee or Bluetooth because they're short range. And essentially, the range could be extended because they're pretty much like based on a mesh network topology. So like meaning all data is routed from one node to another rather than each node sending the data to a central gateway. So I thought it sounded like a cool concept, but it was just very complex. And also, I was expecting for my devices to um, go into deep sleep mode throughout the day and just like wake up like when they were needed in order to extend battery life. So ultimately, I decided on LoRaWAN, for a few reasons. So mainly, it has a very long range. So from what I researched, I couldn't really find any IoT protocols that could reach past about 200 feet. So that just about covered the range for some building, but I was just like looking for like a slightly higher range. And the low battery consumption was definitely a plus. And what I really liked was that there was an active and global community established. So there's actually a pretty large group. I'll talk a bit more about them later, but they're called the Things Network, and their forums and meetup group were very helpful in getting everything working. And essentially, one drawback compared to other protocols like Wi-Fi and Bluetooth is that the payload for LoRa packets are very small. So they're about, you can send about 100 bytes per minute. So like that works for like small sensor values. Well, that works for sensor values and like small text messages, but that won't really work for like large data payloads like images and audio. So here we just have like a high level view of how the whole system works. So starting from the left-hand side, we have a variety of sensors. So as you see, it could be any types of temperature, sound, humidity. And each sensor is wired directly to a microcontroller, which I will refer to as an end node. So as once sensor data payloads are collected and formatted, the next step is to essentially forward the payload from the end node to the gateway. And this gateway is expected to have access to both power and internet and being a more stable environment. So I'll talk a bit about the hardware and software for both of these build types, and then I'll come back to the architecture. So the next step was to essentially research the hardware requirements. So as I mentioned in the previous slide, so our build was set to contain a gateway and one or more end nodes. So I decided on a pretty popular gateway build. Essentially, it was assembled from a Raspberry Pi, which you can see in the middle, and also LoRa concentrator module. Um, so essentially, initially I used wires to connect the relevant gateway pins to the GPIO, but it was like very difficult to debug and things could become like unplugged very easily. So I switched over to a PCB shield, which you can see on the left-hand corner. So this is what the final result looked like after setting up with the PCB shield. And so essentially I just like had to solder the gateway shield to the LoRa module and then insert some header pins to connect to the Pi. Okay, so after getting the hardware all set up, essentially I was able to then log into the Raspberry Pi and install an application called Packet Forwarder. And essentially what this does is it just like boots up the LoRa concentrator module, and it allows for it to wait for LoRa, incoming LoRa packets. So essentially like any end nodes that are within range of the gateway, as they broadcast messages, it will be picked up by this application. So the arguments that I had to provide to this application, I had to say essentially like I had to specify where the reset pin is, and I also had to place the credentials in this packet forwarder YAML file.
Kalonji, quick question for you.
Sorry.
When I hear the word packet, I think of unreliable delivery and a fire and forget type model where the gateway may or may not get the packet. Is that what we're talking about here as well?
Yes, essentially.
Okay.
Okay, so just moving forward. So essentially like when the gateway was all connected, then the next step was to assemble an end node to actually collect sensor data. So in general, these end nodes are small microcontrollers, and you can generally use the Arduino IDE to place a C script on it, and essentially, so it runs the C program in a loop. And essentially, what that can do is that can sample the raw sensor data, it can format it, it can add additional metadata, such as like time, location, and sensor type. And then it can basically just like send that off using the LoRa rate, the attached LoRa radio. And so these are typically very like low power resource constrained devices. So they should be powerful enough just to like run some basic edge analysis, but in many cases, at least in my case, they're probably going to be in the field running on battery power. So it'd be best to keep edge processing to a minimum. Because that would, of course, like drain the battery more quickly. So essentially, there are two main choices I was seeing, at least in the message board. So one was the Adafruit LoRa Feather, and the other was the Arduino Uno. And so I decided on the Feather mostly because it had a good range and it had like a lot of support. And I also like that it had the option to go into deep sleep mode. So that could drastically increase the battery lifespan, as the end node can just like simply like wake up, collect some data, send it off, and go back to sleep for however long. And so this is just like kind of a schematic of an end node that I have connected to a sound sensor. So it's definitely not, it does look kind of complex, but it definitely like looks more complex than it actually is. So essentially like the main cables that we want to focus on here are the cables providing power to the sound sensor. So if you look at the bottom left, then you'll see a red line, which is essentially providing 3 volts. And then we have ground, which is essentially like a negative charge. So that provides that provides power to the sound sensor. And then we have a yellow line, which allows for us to actually like sample the sound sensor as needed. And it's also worth noting that you can attach up to, I believe, 6 analog sensors at a time. But just keep in mind that like the more you attach, the faster your battery will die. So this is just like an example of the code snippet that I generally run on my end nodes. So starting from like the highlighted sections, we're just like defining a few variables to specify. So here we're showing that the sound pin is feeding data into the A0 pin, which again you can see here at the lower left where the yellow wire is connected. So after we specified the sound pin, then we can also specify essentially like how often we would like to sample the sensor. So in this case, we're measuring sound levels approximately every second, or 1.1 seconds. And each sample is like 1 byte, 1 byte. And the reason for this is we want to stay below the regulations. So essentially, like there's a duty cycle, basically saying each end node can broadcast about 100 bytes per minute. So we just like want to stay below those regulations. And lines 154 through 159 are running in a loop, and so essentially it's constantly like sampling the sound sensor until 50 sensor values have been collected in an array. And once the array is full, then it gets sent off with the last line, the set transmit data. Okay, so just back to the architecture. So essentially, after assembling the hardware and configuring the software, we should have sensor data coming into our gateway. So the next step essentially would be to get sensor data into the cloud so we can save and analyze the data. So before doing this, the raw LoRaWAN packets that are received by the gateway, they essentially need to be processed by a LoRaWAN server stack or application. So essentially, this ensures that the packets are in order, we're not processing duplicate packets, and that they are all coming from authenticated end nodes. So once the packets are validated, they're then translated to a readable format. So this stack can either be ran directly on the gateway or in the cloud. So it's non-trivial to actually like set up your own LoRaWAN server. So there are a couple like open source offerings, but when I was initially getting started, I opted to use a popular offering called the Things Network. So they're probably one of the largest groups dedicated to getting more LoRa gateways deployed out in the world. And as I mentioned earlier, like their message boards and their meetup group made this building process a lot smoother. So their gateways are public and shared. So essentially, if you don't want to go through the process of buying and building your own gateway, as long as you have like one of the Things Network gateways within range, you can actually just like publish to that. But of course, like in that case, like your data will be publicly accessible as well. And so essentially just like here's like a view of a few messages being received by the Things Network console. Okay, so once we get the data transmitted and processed by the LoRaWAN stack, we want to actually forward the data to cloud services so we can actually like import it into an application and basically just like run it through various cloud services. So one of the more popular IoT messaging protocols in the industry is called MQTT. So essentially, it's a very like scalable, lightweight protocol which clients can both publish and subscribe. So essentially, each subscriber needs information on where the MQTT broker is. So essentially, like how to access it, what the endpoint is, the port, and etc. Also, like how to authenticate to it, and which channel to listen to. So essentially, every time, and when other messages, then those messages are routed to the valid subscribers. So yeah, another good thing about the Things network. So it essentially like allows for us to receive validated messages through an MQTT message bus. So I know it's a bit hard to read, but essentially in the screenshot above, I have the MQTT process, and it's just like running, and it's subscribed and listening for messages in the terminal. So as these messages come in, the data collected by the end node can be seen in the underlying payload raw section. Okay, so at this point, we should be able to directly pull the data into various cloud services so that we can actually like make a application around it. So in general, I like to publish my data streams to the Watson IoT platform via that same MQTT protocol. So as data is streamed into the platform, we can get a high-level visual by using the built-in graphs functionality, which is also referred to as boards. So in addition to interactive graphs, we can also use plugins to directly bind to other services. So one popular setup is the Historian plugin. And essentially what that does is every time an MQTT message is received by the broker, the data payload is persisted into a cloud database. Okay, so once we were able to figure out exactly like how to get our sensor data up into the cloud, then we built out a few use cases. So this is an example of one of the use cases we continued on. This is for asset tracking. So the idea here is that each end node has a GPS tag connected to it, and it of course can have additional sensors connected to it as well. So as the location is updated, the coordinates are broadcasted to the Watson IoT platform through that MQTT message and persisted in the cloud and database. And in addition to the message being saved in the database, the project also includes a web UI. And essentially this web UI also subscribes to the IoT platform for location messages, and it essentially updates the location of each asset as they change. So essentially like this is the front end UI of the pattern. So it's like very basic, but allows for you to see the location of end nodes in real time and also to trace back through their path. So originally like one of the main use cases before we moved it to, we made it more general. The idea was behind tracking zebras in the wild. So essentially, I believe Watson IoT has a partnership with I believe it's some of the anti-poaching efforts in Botswana. And essentially what they do is they put a collar on various animals, and this collar has both a LoRa radio as well as like a GPS tracker and accelerometer. And so based off of how the animal is moving, then anti-poaching soldiers can essentially determine like whether there are poachers like in the area. And this is another LoRaWAN based use case we worked on recently. This is a bit closer to the smart city use case. So the idea here is that we can have several nodes distributed around a city. And so each node has air quality sensors attached and samples the air quality about every 30 seconds or so. So as data gets saved to the database, we can import it into Watson Studio and do like some high level analysis using a Jupyter notebook. Yeah, so this is just like using, this is essentially using a Python package called scikit-learn, and essentially like that allows you to handle large level data sets and also generate graphs. Oh yeah, and also we try to make these color patterns a bit interchangeable. So this is actually compatible with the previous color pattern with the asset tracking one. So we were able to actually generate a CSV file and then just load it directly into the mapping pattern. Yeah, so I think that's pretty much all I have for now.
Hey, Kalonji, a question for you. When you were first talking about collecting the sensor data in the building, you mentioned about taking sensor readings and buffering up 50 at a time and sending them out as one packet. Do you see that a lot? And if so, it seems like there has to be a step somewhere in the architecture where you sort of unpack the packet, so to speak, to get sort of your discrete data items. At what point in the architecture would that happen?
So that's actually handled by the LoRaWAN server. So that would all be handled by the Things network in this case, and and essentially once that's processed, then the Things network just sends you back your data as it was sent out originally.
And so, but you have to write the code that plugs into that server to do that unpacking, right?
Oh no. No. Essentially, all you have to do is let me see if I can go back. So essentially, this packet forwarder service, it just sits and listens for incoming LoRaWAN packets, and as soon as they're received and they're sent up to the Things network or to whichever LoRaWAN server you might be using, and essentially that's where the packets are then rearranged and decrypted and so on.
Okay, thanks.
Yeah, no problem. So I wanted to see, are there any other questions? And I can also send all this information out as well.
Okay, let me just check. No, we don't have any additional questions about the architecture.
Okay.
Anything else for us today?
No, I think that's pretty much it for now.
Okay, well, I certainly appreciate that. We did get Kalonji's slides up on the event page. So once again, that's the first link in the description field below the player. So visit the event page, and you can download the slides and get Kalonji's contact info and all that stuff if you have additional questions. So with that, I think we will wrap things up, but I want to thank you, Kalonji, for doing this today, and look forward to hearing more about this protocol and your Internet of Things work in the future. So thank you so much.
Oh, no problem. No problem at all.
All right. Take care. Bye-bye.
Bye.